Dear students, let us continue our discussion on vector addition. Now we'll discuss about the properties of vector addition. In this video, we'll discuss three properties of vector addition. One is commutative property, associative property, and distributive property. Okay, so let us first tell you about the commutative property. Commutative property. Okay, so let us first tell you about the statement and then we'll move to the proof also. Okay, so if you have two vectors a and b, and if you add these two vectors, that is a plus b, that will be same as b plus a. That is, the addition of two vectors will commute each other. A plus b is same as b plus a. Now how can you prove this result? So let us take a parallelogram. That will be very easy for you if you want to prove this. So suppose we have a parallelogram, something like this, and you know the vector addition by using parallelogram law. So suppose this is your vector a and this is your vector b, and you know the resultant vector of a and b will be the diagonal adjacent to a and b, that is this. Okay, so this is your a plus b, very simple. But you know, if this vector is b, then this vector is also b, because it is the opposite side of a parallelogram. So now you use the triangle law, then you will get the same result, that is a and b are two vectors which are consecutively present on the two sides of a triangle. So the third side in opposite direction will give you the resultant, that is a plus b. So this diagonal that I am showing here by using the red line is the addition of a and b. But if you see that as this is a parallelogram and the two sides are always equal, so this side represent b, and if this side represent b, then obviously that will be same for a vector also, because this sides present a, so this sides will also present a, isn't it? Now let us take a different look. That first what we have done, we have add a and b in this direction and we will get this, so that we can write a plus b. But if you look it in different way, in this direction first b then a, again by using triangle law you can write this sides will represent you b plus a. So you can see the same diagonal that I have shown here by using a red line. Once it represents a plus b, and then in the next look it represents b plus a. So if you move in this direction you will get a plus b, but if you move in this direction you will get b plus a, and that is the same diagonal. So you can write a plus b equal to b plus a. So this is very simple to prove that vector addition follow commutative property. Now let us talk about the associative property also. Number 2, that is associative property. Okay, associative property. Again first let me tell you the statement, what is the associative property. So if you have three vector now, one is a, another is b, and another is c. Now first let add a plus b, then c, and you will get the same result if you add first b plus c then a. Again we can prove this result by geometry simply. Suppose we have vector a something like this, vector b and vector c, suppose. So this is our vector a, this is our vector b, and this is our vector c. Okay, now what you want to do, let us first add a plus b. So if you want to add a plus b, the resultant vector will be this, by using triangle again. So this is your a plus b. So now if you want to add c, so first a plus b then c. So your resultant will be now this. So this is your a plus b plus c. Now what you want to do, you want to do b plus c first. Please keep in mind, from the right hand side you want to do b plus c first. So this is your b and this is your c. So what will be your b plus c? This will be your b plus c, you can see. So this is your b plus c now. Now what you want to do, you want to join a and b plus c. So now this is your a and that black line is showing your b plus c. So now this is your a and this is your b plus c. So what will be the resultant vector of a and b plus c? That is again this red line. So now this red line is showing a plus b plus c. Now you can understand that this red line showing a plus b plus c and a plus b plus c. So you can write, obviously geometrically, you can prove in this way that a plus b plus c is same as a plus b plus c. So this is how you can prove the associative property of vector addition. Similarly, one more important property is that the distributive property. Number 3 is your distributive property. Suppose you have two vectors again, a and b, and if you multiply a scalar number with this, suppose you have vector a and b, and if you have a scalar number n, something like this, and then that will be same as na plus nb. N will be distributed individually to a and b. So this is your distributive property, and you can prove this if you want, but I think there is no need to prove this because this can not be proved by geometrically. This can be proved by analytically. What you have to do, you have to first, so let me prove you, okay, prove this thing. Let me show you the proof also. So you have to prove for left hand side and right hand side. What you can do here, what is the resultant? You have to, when you have to prove analytically, you have to show the magnitude of the resultant as well as the direction of the resultant. So what is the magnitude of left hand side and what is the magnitude of right hand side? So the magnitude of left hand side will be resultant, resultant is nothing but square root of a square plus b square plus 2ab cos theta. So it will be n multiplied by, because n is a scalar number, 2ab cos theta. Similarly, right hand side you have r dash, and that will be square root of na square plus na whole nb whole square plus 2 multiplied by na multiplied by nb, and that is same. You can see if you can take common n, so n square root of, with n square n square b square, here is all n square, so if you take n square common, then it will be n outside, so it will be a square plus b square, sorry, one is cos theta also here, so it will be 2ab cos theta. Now you can see that this r and r dash is same. So the magnitude is same. Similarly, you can prove the directions also by using the tan alpha. So you know what is tan alpha. Tan alpha is nothing but if you want to see the direction of a plus b, and alpha is the angle made by a with the resultant, something like this. If you have, this is your a, suppose, and this is your b. Now if this is your resultant, that is a plus b. Now what is the direction of a plus b? Because the direction of a plus b will be same as the direction of n into a plus b, because n is a scalar quantity. So what is the direction of a plus b? If this is the direction alpha, so it will be just b. If this is theta, let me write it as theta. Sorry, this is alpha, but the angle between a and b is theta. Let us take. So it will be just b sin theta upon a plus b cos theta. So this will be tan alpha. But if you write this is na and this is nb, then what will be tan alpha? That is for right hand side. So in this case, tan alpha will be nb sin theta divided by na plus nb cos theta. And if you take common n, then n will be cancelled out, so it will be b sin theta. If you take it alpha dash, then it is a plus b cos theta. So you can see that alpha is equal to alpha dash. So this is how you can prove this. You cannot prove it geometrically, because geometrically it is obvious. It is obvious because whenever you will multiply a scalar number with a vector, then obviously the direction will not be changed. So what will be the direction of a plus b? Will be same as the direction of na plus nb. But you can analytically prove in this way. First you have to prove the magnitudes, then you have to prove the direction. The magnitude and direction both are equal, then obviously the vector which is in left hand side will be same as the vector which is in right hand side. This is how you can prove this distributive property also. Okay.